Hi, I'm David,
And I'm Alex.
and our project is on partial derivatives. In class this year, we learned about regular derivatives, and that allows us to take the slope of a curve at any point on the curve. So if I have this rope, for example, even if it's changing, and I have the equation, I can find the slope of the rope at any point with the equation of the rope.
But this changes in 3 dimensions. For example, if we want to take the derivative of the soccer ball, there are many different options. This could be one of the derivatives, but so could this or this. So how are we going to find that?
In essence, what we're looking to do is find a plane that is tangent to the surface at a given point, like this Radiohead CD. But now you may be asking yourself, a ball, it's like a pretty perfect figure, right? Could we do this with a different figure? Let's go to the gym to find out.
Let's go.
This is Alex. He has huge biceps. Let's see if we can find the derivative of those huge biceps. If we use the ruler, which is just one dimensions, we have options because we can go like this, but also like this. Like with the ball, we're gonna have to find the derivative of the surface with a plane.
So here we have a multivariable function. Notice how it's not a parametric, so it takes in 2 variables and spits out 1 output. So here we have the multivariable function 4x squared times y cubed. Now, how are we going to find the derivative of this function? Well, it's actually not going to be in one step. So what we did before is we took the derivative in one plane. So therefore, we're going to need 2 equations. One while maintaining y as a constant, and the other while maintaining x as a constant.
Go ahead.
Okay. So now that we're maintaining, now let's take the partial derivative of x while assuming that y is constant. So that is our first partial derivative, 8x times y cubed. And now with respect to y, so assuming that x is constant. And those are our 2 partial derivatives.
If it helps you to understand, in this case, we can just assume that y cubed is a constant like 4 or 5, or just a. And so it's actually not going to be changed when you find the derivative with respect to x. Here is another practice problem. Feel free to pause the video now, and if not, let's just get right into it. For this problem, it's actually useful to rewrite x over y as x times y to the negative first power. We'll see why that is in a second. And like we did before, we're going to have one derivative with respect to x keeping y constant, and one derivative with respect to y keeping x constant. Let's just start with x. And we know that the derivative of x is simply 1, so this will be 1 times y to the negative first power, which is just y to the negative first power. And down here, we're going to have x times y to the negative first power, and we want to keep x constant. So, we know the derivative of y to the negative first power is negative y to the negative second power times x. And that will just leave us with negative x times y to the negative second power. Another thing that's really important when it comes to partial derivatives is something called Clairaut's theorem. And what it essentially states is that if you take the derivative of this with respect to x, and then after you take the resultant with respect to y, you'll get the same result as if you take this with respect to y, and then the resultant take that with respect to x. So let me just demonstrate what that means. Let's say I want to start this one with taking the derivative with respect to y, leaving x constant. So what I would say is, back what it says here, this is equal to 3x cubed, because we leave x constant, times 2 cosine y times negative sine y. Now, let's say I want to take the derivative with respect to x of this resultant here. So not of this equation, but of this resultant here. So then I will be with this. So I will go like that. And now, remember, this is just going to remain constant. I'm going to do take care of this one here. So that becomes 9x squared 2 cosine y times negative sine y. Now, essentially what Clairaut's theorem says is that if I do this backwards, so if I do x first and then y second, I'll get the same result. So let's just verify that. If I start with x, I will start with 9x squared times cosine squared of y. Then, if I take with respect to y of this, I'll end up with, again, 9x squared. And then here, cosine squared y will become 2 cosine y times negative sine of y. Now, while this might seem sort of trivial or intuitive with just 2 variables, something that's interesting is that if I do this infinite amount of time, as long as I have the same number of x's and the same number of y's, this will remain true. So for example, let's say I have a function and I'm going to do, first take it with respect to x, then y, then x again, then y again, then x again, then y again. If I take that same function and I take it with respect to x, then x again, then x again, and I take it with respect to y, then y, and then y again. I've got 3 x's here, 3 x's here, 3 y's here, 3 y's here. This will always equal each other. That's something that's really important. As long as you have x's and x's the same on each side of the equation, and the same thing for the y's, this will always be true. One of the applications of partial derivatives is when we look at neurons and the action potential that it takes for them to send a signal. You remember this is vaguely what a neuron looks like from freshman bio. And in order for a neuron to fire, you have to reach a certain threshold with positive and negative charges that is accomplished through the pumping of sodium and potassium ions through these pumps, which send 2 ions one way and 3 ions the other way. These ions, however, don't flow necessarily at a constant rate, and so neither does the action potential that is needed to send the signal. And one thing that biologists do is they assign one variable to a sodium ion and one variable to a potassium ion, and then they can find the partial derivative of both of those to see when the neuron will actually send the signal with respect to the levels of potassium and sodium and the resulting charges.
So another possible application of partial derivatives and multivariable functions is the weather. So for these models, you take in more than one variable, let's say temperature, humidity, and pressure, and you put them all into your function, and it will spit out the percent probability of precipitation. So partial derivatives here can help us find the change in temperature that might lead to the formation of clouds that might cause it to rain.
Those were just 2 of the very many applications of partial derivatives. In science, it's actually really rare that you have only one variable, and so when you have 2 variables, or as Alex showed, even more than 2 variables, you can use partial derivatives to help you out and get lots of results that are really important for science.
All right, thank you for watching our presentation, guys, and we'll catch you later.